What makes a triangle? Okay, so we've talked about all three of these, plus they're up on the word wall. Angle, side, angle, side, angle, side, and side, side, side. Triangle congruence. Here's a couple of triangles that have the same angle measures and the same side lengths there. And I'm just going to redo this. So two figures are congruent if they can be placed on top of the other and they match up perfectly. The symbol for congruent is that sign. It's equals with a squiggly line over it. Then it says, consider the situation in the year 1778. The future president, George Washington, is a surveyor. He is evaluating two triangular plots of land that he thinks may be congruent. But how can he be sure? He can't cut them out and put them on top of one another. Okay, finally an example of geometry that actually does use some of what we have been learning. So what does he have to measure, what does he have to measure to know if the triangles are congruent? Does he have to measure every side and every angle? In fact, there's an easier way. Based on our experiences with drawing triangles with ruler and protractor, SAS and ASA, and drawing specific triangles, SSS, all these things we've been working on, we can introduce three postulates about triangle congruence. These postulates can help you, the surveyor, determine the fewest measurements he can make and yet still be sure the triangles are congruent. So here's those three postulates. So one, they could measure side, side, side. Triangle congruence postulate. So if three sides of one triangle are congruent, the corresponding sides in another triangle, if three sides of one triangle are congruent to the corresponding sides in another triangle, then the two triangles are congruent. That means if you're given side, 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 then these two triangles are actually the same unique triangle. Continuing on, side, angle, side, congruence postulate says if two sides and the angle in one triangle are congruent to the corresponding sides and angle in another triangle, then the two triangles are congruent, right? And just to be really clear, that's if you have a triangle, it's side, side, and the angle in between. Side, angle, same idea where it's the side in between, right? So if you have an angle, a side, and an angle, it has to be the side in between. If two angles and the included side in one triangle are congruent to the corresponding angles inside in another triangle, then two triangles are congruent. George sketched the two plots he was evaluating and labeled them. If George measured that one triangular plot has measurement of angle A equals 43 degrees, okay, I'm going to take notes as we go. So we say angle A is 43 degrees. Segment AC measures 3.62 miles, so AC is 3.62 miles, might as well. Measure of angle C is 82 degrees, so that's 82 degrees. And the other triangle plot has measure of angle R, 43 degrees. RT, 3.62 miles. And measure of angle T is 82 degrees. Can he be sure the two plots are congruent? If so, according to what triangle congruence postulate? Well, let's look at this. So here we've got an angle, a side, and an angle, and it is the included side, of course, where it's 43, 3.62, and 82. Here we've got the same thing, but in a different spot. So 43 degrees, 3.62 miles, and 82 degrees, right? So same numbers. And if they are in the same, let's see, if they're also the included side to these two angles, we can say, well, if this angle's the same, this side's the same, and this angle is the same, we can say by angle, side, angle congruence postulate, right? That's this one, triangle congruence postulate, that these two are the same. So can you be sure that you're right? Yes. Yes, they're congruent. By angle, side, angle postulate. I should write congruence postulate. Okay, let's check out number 2 here. If George measures that one triangular plot BC, oh, I kind of scribbled letters. Ooh, let me write in a different color so we can keep track of focus of this second idea. So then it says, if George measures that one triangular plot has BC equals 3.2 miles, so BC is 3.2, AC is 4.9, and the measure of angle C is 78. 78. Then the other triangular plot has RT, 4.9. T is 78. And ST is 3.2. Can he be sure the two plots are congruent? If so, according to what congruence postulate? Well, let's see what we've got here. For this one, we've got a side, an angle, and a side. So for triangle ABC, we have side, angle, and side. For triangle, let's call it RST, we're given another side, angle, and side. And we can see that the sides are the same sides, the angles are the same angles, and then the next side is another of the same size, which means it's true. So, yes, they're congruent by side, angle, side congruence postulate. Okay, let's keep going. Now some tricky triangles. You know what? No, it's fine. Tricky triangles. The triangle congruence postulate can be used to determine if two angles are congruent. But they can also be used to determine if a set of measures determines the only... Sorry, they can also be used to determine if a set of measures determines only one triangle. For example, if you are given three sides of a triangle, does that determine only one possible... Sorry, I lost my spot. Does it only determine one possible triangle? It does, because any other triangle with the same three sides would be a congruent triangle. So it talks about triangle uniqueness. Mr. Arnold Buford makes up a set of problems specifying triangles for his students to draw. To give his students something to argue about, he includes some instructions that won't work. Ooh, okay. Try to draw each triangle below. Decide if a unique triangle is determined. If the instructions do determine a unique triangle, state which triangle congruence postulate applies. If the instructions do not determine a unique triangle, explain why not. So let's see. So we have triangle ABC, where we're given... Oh, you know what? It does want us to draw these. Let me grab a piece of paper. Okay, here we go. So we're going to draw a triangle ABC with A equal to 88 degrees. AB is 12 centimeters and B is 110. So let's measure this out real quick. So here's 12 centimeters. So AB being, oops, and I want to just extend this line a little bit. So we'll call this A, we'll call this B. Let's see, angle B is 110. B is 110 degrees. Oops, my protractor's upside down. So line those up. 90, and then wider is 110 right there. So angle B, this is 110 degrees. Okay, and angle A is 88 degrees. So there's, where's 88? 40, 50, 60, 80, 8. And there's 88 degrees. Okay. First of all, is this going to make a triangle? The answer is no. Triangles need for these two rays to intersect at some point. But right now, they're not going towards each other, going away from each other. And the problem is actually that these two angles added up are greater than 180 degrees. And that's a problem. Okay, so this one doesn't work. Let's keep moving. And I'll let you all write down and explain why. I'll explain it with words. You can capture it on your own papers. Okay, we're going to try triangle SAP, where P is 45 degrees and SA is 12 centimeters. So I'm going to draw another 12 centimeters here. Hey, Ben. Hey, what's up? Okay, perfect. I'm just making a geometry video. That's 12 centimeters, and we're gonna call that SA.
How are you feeling these last few weeks?
Then,
I'm sorry.
oh, you're good. And angle P is 45 degrees, but where does angle P go? That we don't know where to put this point of P. It's a mystery. It could go here, it could go there, it could go anywhere. So we don't know where to put P. Okay. We'll keep going. Triangle PEA. Let's see, we've got measure of angle P is 52 degrees, measure of angle E is 105, measure of angle A is 23 degrees. So, what we can do, let's just start off with some line segment. And we know, let's see, we'll start off with angle P is 52 degrees. So we'll just mark a P. And we can draw a 52 degree angle. 10, 20, 30, 40, 52. See, I shouldn't have drawn it. That's not a point, that's just a mark. Okay, then here's 52 degrees. And then our next thing we have is measure of angle E. But do we measure the angle? Our right E is 105 degrees, so do we measure it starting there, or do we measure it starting here? Do we measure the angle starting here? We don't know how far away to put P, the points P and E. So that's another triangle we can't draw. Okay. Triangle nut. Flip the page around. Okay, we've got, let's see. Okay. We've got, let's start off drawing just a line. Drink. We'll do 5 centimeters. So, there's 5 centimeters, and we can call that NU. We know the angle between NU, or the angle N is equal to 105 degrees. Oh, am I going to be able to fit that? Ah, just barely. Great. So then we'll line this up. And then here's 0, 105. Wow, how lucky is that? Okay, so then this is our 105 degree line. And we know we want, this is going to be point T along here somewhere, which is 6.6 centimeters. So let's measure our 6.6 centimeters. Oh man, I'm off the page. That's okay. I'm going to go for it anyways. So we're up here. And if we know that NU is 5 centimeters, and NT, T is all the way up there, is 6.6 centimeters, we can finally complete a triangle. Oh, that's so great, by just connecting those two dots. And that makes sense, right? Because that's side angle side. We can do it. Okay, we've got our first triangle that works. How many more do we got? Oh, 3 more. I hope you're all really enjoying this video. By the way, Ben came in here and talked with me earlier. He says hi to everybody. Okay, next up, triangle QED. Miles? Whoa. Okay, first of all, I'm not drawing miles. I'm going to convert these miles to centimeters and just draw a scale model. So let's start off with 7 centimeters. So we're going to start there, draw our 7 centimeters, and that's QD. So here's Q, this is point D. Then let's draw QE, which is 4 miles, which I'm going to convert, of course, to centimeters. But for this one, I'm going to use my compass, and I'm going to need a 4 centimeter measurement. Okay, so then I'll take my point to make the center on Q, and then draw some arc that hopefully meets in between. And then, oh, you know what, I'm going to actually stem this down because I see a problem. Point Q, or ED, is 2 centimeters. Okay, so if I measure 2 centimeters with my compass, I can put it on point D and draw my circle from there. And can you all see our problem? Q, let's see. So that would be QE and ED are too small to make a triangle, or QD is too big, meaning these two sides added up are smaller than this one side. So for triangles to exist, you should be able to add up 2 sides and it'd be bigger than the other for all 3 sides. So this one doesn't work because the sides are too small. Some of the lengths are too small. It's called the triangle inequality postulate. Okay, triangle PAL. We know a PA and we know an AL, so let's draw a PA. Do you all know? Can you tell yet if we can draw this or not? Hopefully you can already see that if we're given 10 centimeters, for PA, and we know AL is 4 centimeters, but in what direction? So like, is it going to be 4 centimeters like that, like that, like that, like that? We don't know the angle, so we can't draw the triangle. Okay, and then we're finishing up. And I'm going to flip my page over here. And we're going to draw a triangle end. Man, I love when they name it stuff like this. So we're going to start off by drawing a 12. Am I still on the screen? Yeah, I haven't been looking. Hopefully this hasn't been out of focus the whole time. 12, that's EN, is 12 centimeters. Then
I'm almost done.
Then ED is 6.3 centimeters. Let's see, that's 6.123. Okay, that's ED, so I'll put my pointy bit on E. And I'll draw my arc. So ED is 6.3 and ND is 5.9, so just a little bit smaller. So let me measure out 5.9. Just a little bit longer. Looks great. So ND is 5.9. Hey, and we've got an intersection, which means, you guessed it, we've got a triangle. So where they intersect there is going to be point D. And now we can connect E to D and point N to point D. And that one works. Okay, thanks for watching.